So, um, in the 50 milliseconds it takes for you to blink, an enterprise payment system has already verified your identity, mathematically signed a digital vault key, locked a database ledger, and, authorized the movement of actual human wealth.
Yeah, it's pretty wild to think about.
Right. And the crazy part is it does all of this without a single human password. It's just utilizing this sprawling, invisible city of microservices that are all communicating in real time.
It really is the absolute definition of a black box for most people. I mean, you click buy, and you simply trust that the architecture knows how to sequence those millions of computational steps flawlessly.
Exactly. But we are going to crack that black box wide open today. Welcome to another deep dive. Today's mission is, well, we've got our hands on a really comprehensive slide deck, and it maps out the exact architecture used to build, test, and scale a production payment processor.
Right. It's titled Enterprise API Architecture with Laravel.
Yeah, and our goal here is to translate this dense, highly structural schematic into a clear mental model of how modern digital money actually moves. Because whether you're a developer or just insanely curious, we want you to understand how a system achieves speed, security, and scale all at once.
Because in an enterprise financial application, I mean, sacrificing any one of those three is catastrophic.
Oh, absolutely.
If the system is secure but relies on synchronous blocking operations, users just end up staring at a loading spinner, right? And they abandon their carts.
Nobody has the patience for that anymore.
Exactly. But if it's fast and poorly authenticated, malicious actors just drain the ledgers. And, if it's both fast and secure but tightly coupled in its infrastructure, the entire platform just collapses under the traffic spike of something like a Black Friday sale.
Okay, let's unpack this blueprint. Before we get into the individual gears like the endpoints and database tables, the source material starts with this grand schematic. It's this striking 3D cube diagram mapping out the guiding principle.
Yeah, the factory floor, basically.
Right. And the architecture is built entirely around interconnected microservices and databases, which, looking at the notes, is a massive departure from the monolithic applications of the past.
It is a huge shift. I mean, in a monolith, your authentication logic, your payment processing, your user profiles, they basically all share the exact same memory space. They run as one single massive process.
Which sounds like it would be a nightmare to manage.
Oh, it creates a terrifying deployment scenario. Think about it. If you want to update just the machine learning model used for fraud detection, you have to redeploy the entire application.
Oh, wow. So everything goes offline.
Everything. And if that deployment contains a bug, like a memory leak, it doesn't just take down the fraud detection, it crashes the payment gateway and the authentication service right along with it. The blast radius is the entire company.
That is terrifying. So this blueprint avoids that by taking a decoupled approach. We have an auth service running OAuth 2 and JWTs,
Right.
and then separate payment gateways connecting to Stripe and PayPal.
Right, isolated containers.
Exactly. Then there are transaction ledgers running on PostgreSQL, reporting engines tied to a data warehouse, and even fraud detection is split into two distinct models, a machine learning model and a reinforcement learning model.
And what's fascinating here is the communication layer between all these decoupled services. The document really emphasizes that they don't just rely on traditional HTTP requests to talk to each other.
I noticed that they're synced via Kafka event streams and webhooks. And I mean, a traditional API request is essentially like a phone call, right?
Yeah, that's a good way to put it.
Like the auth service calls the ledger service,
Yeah.
and it literally has to wait on the line until the ledger answers and confirms the data was received. That blocks the whole process.
Right, it blocks the thread. But Kafka's fundamentally different. It operates on a publish and subscribe model.
So how does that work in practice?
Well, think of Kafka as an incredibly high throughput distributed log file. When the payment gateway processes a transaction, it doesn't call the fraud detection service directly. It simply publishes an event, a message saying transaction 123 occurred to a specific Kafka topic,
Yeah.
and then the payment gateway just immediately moves on to the next user. It does not wait.
Okay, is this like a high-end restaurant kitchen?
Yeah.
You have the prep station, which is auth, the mainline cooks handling the payment gateway,
Yeah.
the expediter calling out orders, that's Kafka, and the manager in the back tracking inventory, which is the data warehouse.
That is a perfect analogy.
Right, because if the inventory guy gets behind, it absolutely shouldn't stop the chef from cooking the steak.
Exactly. And the fraud detection service is acting as a consumer, right? It's just subscribed to that Kafka topic, so it reads the message whenever it's ready.
So the chef cooks, the expediter shouts the order, and the inventory guy just listens and updates his clipboard whenever he has a second.
Yeah, and this is where the split between those two fraud models, the machine learning and reinforcement learning models, becomes brilliant.
How so?
Well, the ML model might be looking for known anomaly patterns, like a sudden spike in purchases from a new IP address. It can process that in milliseconds.
Fast and easy.
Right. But the reinforcement learning model is designed to adapt to entirely new, unseen fraud tactics. It does that by continuously updating its own parameters based on live feedback loops, and that takes much heavier computation.
I see.
So by using Kafka, both models can consume the exact same transaction event simultaneously, but at their own independent speeds without ever bottlenecking the actual user's checkout process.
Wait, hold on. If the fraud detection is consuming this data asynchronously, like after the transaction has already been published, what happens if it actually detects fraud?
Ah, right.
Because the user already clicked buy, the system didn't wait, so the payment is already processing. Isn't that a huge architectural flaw?
That is a great catch, and it raises an important question about eventual consistency versus strong consistency.
Okay, what does that mean?
Well, in this design, the initial Kafka event might be a payment authorized event, not a funds settled event.
Oh, I see the difference.
Right. So the fraud system consumes the authorization, and if it flags a critical anomaly, it publishes a counter event, basically a hold payment command, right back to the stream.
Now,
And the ledger service consumes that hold command before it actually settles the funds with the banking network. It's this highly choreographed dance of state machines communicating through immutable logs.
it's incredible. So the next time you, the listener, buy something online and it processes instantly, just remember this exact symphony is playing out behind the scenes.
Yeah. Thousands of times a second.
And to organize all of this, the source material breaks the request lifecycle down into 5 distinct pillars: security and access, core logic, quality assurance, asynchronous processes, and infrastructure.
Every single user action travels through that exact 5-pillar gauntlet.
Right, so let's get into the digital restaurant. First, you have to get past the bouncer. Pillar 1, security and authentication.
The perimeter defense.
And the document outlines a truly radical architectural choice here. Under their authentication typology, they have completely eliminated traditional passwords.
Completely.
And standard hash password auth is explicitly marked as not used in this stack. No passwords at all.
Which is incredibly smart. Passwords are historically the most compromised vector in any enterprise system. I mean, users recycle them across multiple platforms constantly.
I'll do it, yeah.
Right, and if a totally unrelated form gets breached and leaks a user's password, attackers will immediately use automated credential stuffing to try that exact same password on this payment processor. By removing passwords entirely, you eliminate credential stuffing at the root.
So for human dashboard users, the system relies entirely on magic links, which the document says have low UX friction. The slide breaks down the lifecycle into 4 steps. Step 1 is request initiation.
Right.
The user enters their email on the auth route. The system then utilizes a cryptographically secure pseudo-random number generator to create a unique token, which it stores in the Magic Links database table.
And it's important to note the anatomy of that token. It's not just some random string of letters. It's a high entropy key tied to an explicit expiration window, often just 10 or 15 minutes, and it's cryptographically bound to that specific user's database ID.
Right, highly secure. So step 2 is dispatch. A class called Welcome Mail sends an email containing a URL with that token embedded right in it as a query parameter.
Yep.
Then step 3 is verification. The user clicks the link, the system looks up the token, verifies the cryptographic signature, checks the timestamp to make sure it hasn't expired, and authenticates the user.
And then comes step 4, which is the absolute linchpin of the whole thing, the access and cleanup phase. The document literally mandates token is permanently deleted to prevent reuse.
Because if you don't immediately destroy the token the millisecond it's verified, you leave yourself wide open to replay attacks, right?
Exactly. If a malicious actor intercepts network traffic or, even just gains access to the user's browser history later that day, they would find that magic link URL.
Oh, right. The URL is just sitting there in the history.
Yeah. And if the token remained valid in the database, clicking that link would immediately bypass all security and drop the attacker straight into an authenticated session. The hard deletion is what creates a strict one-time use state.
Wait, what if someone's email is compromised? Doesn't the magic link just hand over the keys to the kingdom? I mean, we're talking about money here. Is low UX friction actually always better than high friction?
Well, if an email account is compromised, you do have a severe issue. But think about standard password resets. If an attacker has your email, they just click Forgot Password on a traditional system anyway.
Oh, that's true. They get a reset link, which is basically a magic link.
Exactly. The magic link just removes the illusion of security that a recycled password provides, while massively improving the user experience for the 99.9% of legitimate logins.
Okay, but I have to push back on the UX a bit here. What if the user double-clicks the link in their email?
Yeah.
My dad double-clicks everything.
Yeah, it happens all the time.
So the first click verifies the token and deletes it. The second click, happening literally a millisecond later, hits the server, looks for the token, finds nothing, and throws an error, leaving the user confused and locked out.
So that is a classic race condition, and enterprise systems mitigate it at the database transaction level.
How does that work?
When the first click hits the server, the database places a row-level lock on that specific token during the read process. It verifies it, authenticates the session, and issues the deletion.
Okay.
If the second click arrives while the first is still processing, it hits that database lock and actually waits.
Oh, it just queues up.
Right. And by the time the lock releases, the row is gone, and the server can gracefully return a "you're already logged in" response rather than a hard, confusing failure.
That makes total sense. So it handles human error perfectly.
Yeah.
But magic links are only viable for human beings with email inboxes. What about automated systems?
Right, the server-to-server communication.
Yeah, because a massive part of this architecture relies on automated clients hitting the API. They obviously can't sit around waiting for an email.
Which brings us to Sanctum API tokens. This is the zero-friction layer for automated clients, but it requires an entirely different cryptographic approach.
Right. The slide shows a Sanctum token management interface utilizing long-lived secret and public key pairs passed in the HTTP headers. It specifies authorization, bearer followed by the key,
Yep.
and it explicitly separates the roles of these keys. The secret key handles critical backend operations like actually initiating a payment, and that's managed in a high token table. The public key is safe for the front-end client code and is only used for basic operations.
And if we connect this to the bigger picture of cryptographic security, exposing the secret key to the front end is literally the equivalent of handing out the master code to the bank vault.
Because the front end is just running on a user's device, right?
Exactly. The front end, whether it's the user's web browser or a mobile app, is fundamentally an untrusted environment. Anyone can just open Chrome Developer Tools and read the local storage or look at the memory state.
Oh, wow. So if a developer mistakenly stores the secret key in the browser's local storage, a cross-site scripting attack, an XSS vulnerability, could allow a malicious script to just read that key and beam it directly to an attacker's server.
Yes. And with that secret key, the attacker can mathematically sign requests masquerading as the user, bypassing the entire auth service.
That's a nightmare.
It is. This is why the document so strongly emphasizes using the public key for front-end queries. The public key is like the address to the bank. It can ask the server, hey, what is the balance of this account? And the server verifies the public key is authorized to read that specific data.
But it can't move the money.
Right. If the public key attempts to send a command saying, transfer $500, the server's core logic checks the signature, sees it lacks the cryptographic hash of the secret key, and just outright rejects it with a 403 forbidden.
And I noticed that the secret key isn't even stored in plain text in the database, like in that token table.
Yeah.
The Laravel framework runs it through a SHA-256 hashing algorithm before saving it.
Which is a critical defense mechanism. Let's say an attacker manages to execute a SQL injection and dumps the entire Hitoken database table. They don't actually get the real secret keys.
They just get the hash.
Exactly. They get an irreversible cryptographic hash. The server only ever sees the real secret key once, the exact moment it is generated and shown to the developer to copy down. After that, the server just hashes whatever incoming key the client provides and compares it to the stored hash.
So the security perimeter is fully established. We've got no passwords, zero knowledge storage of API keys, and asymmetric authorization.
The bouncer is doing their job.
Right, so once a request actually makes it past this bouncer, it drops into the second pillar, core logic. This is the brains and the memory of the operation.
The domain where the actual business requirements are executed.
And according to the source, the database topology here relies on eloquent ORM mapping to MariaDB. Now, earlier we talked about PostgreSQL being used for the transaction ledgers, but the core relational topology mapped out in this specific diagram, like the user profiles, the bank details, is running on MariaDB.
Right. Why two different databases, right?
Exactly. Why split them up?
This polyglot persistence model is actually standard for enterprise scale. You leverage the specific strengths of different database engines. PostgreSQL is unparalleled for complex ledger operations. It handles concurrency and strict ACID compliance, atomicity, consistency, isolation, durability.
Which is non-negotiable for moving real money.
Exactly. You cannot have a transaction partially fail. But MariaDB, on the other hand, provides incredibly fast read replicas for the massive web of relational data.
And looking at that relational web, the user table sits right at the center. It links via foreign keys to bank details, transaction, payment, and withdrawal. It's basically the anchor for everything you do online. Every time you link a bank account or make a withdrawal, your user is acting as the anchor in a massive web of tables just like this.
Yep. And to interact with this web, they use eloquent ORM.
Right, ORM stands for Object Relational Mapper, which, if I understand correctly, means instead of writing raw SQL strings like select from users where id opers 5, developers write PHP code using the active record pattern.
Exactly.
They interact with a user object in the code, and the ORM translates that into the highly optimized SQL query under the hood.
The active record pattern in Eloquent is amazing because it abstracts away the immense complexity of database interactions. But it also introduces a significant risk known as the N+1 query problem. Have you heard of that?
I've heard the term, but I'm not totally sure how it works.
Okay, so imagine a developer asks the ORM to retrieve 50 recent payments, right? And then they loop through those 50 payments in the code to find the associated user email for each one.
Okay, makes sense.
A naive ORM implementation will execute one query to get the payments, and then 50 individual queries inside the loop to get the users.
Wait, 51 queries instead of just joining the tables in one query.
Yes, 51 queries.
That would absolutely destroy the database performance at scale.
It would bring it to its knees, which is why an enterprise architecture utilizing Eloquent mandates strict eager loading. The developer must explicitly instruct the ORM to preload the relational data in a single, complex SQL join before the loop ever even executes.
Uh-huh. Okay, and we actually see this exact logic sequence mapped out in the UML sequence diagram for a payment. It is a highly choreographed two-step dance.
Let's walk through it.
Okay, first, the client app sends a POC request to a P1 payment to initiate with the amount. The API talks to MariaDB to create a pending record and returns a checkout error. Then the client goes to that URL, enters their details, and sends a second POST request to a P1 payment charge, which updates the database to completed.
And this two-step initialization is a fundamental pattern for distributed transactions. By creating the pending record first, the system establishes a unique identifier, an idempotency key, for that specific intent to pay.
An idempotency key ensures that no matter how many times a request is duplicated, the outcome remains the same.
Right.
Yes.
Think about what happens if the user's mobile network drops out right as they hit the final charge button.
Oh, they panic and mash the button 3 more times. I've done that.
Exactly. We all have. If the system wasn't idempotent, the API might process 3 distinct charges, draining your bank account.
Yikes.
But because the sequence requires that initial pending record, the API looks at the idempotency key attached to all 3 of those chaotic clicks. It processes the first one, transitions the state in MariaDB from pending to completed.
And the other clicks.
When the subsequent clicks arrive milliseconds later, the database simply responds, hey, this transaction is already completed. It prevents duplicate charges mathematically.
Here's where it gets really interesting, though, because building these endpoints and managing idempotency keys is complex enough. But documenting how other developers are supposed to use these endpoints is usually an absolute nightmare.
Ooh, it's the worst part of the job. Integration failures caused by outdated API documentation cost the industry billions in lost engineering hours.
Because the code drifts out of sync with the documentation the exact moment an engineer updates a parameter and forgets to update the manual.
Exactly.
Well, the blueprint solves this with automated OpenAPI generation using a tool called Scramble. The slide shows how PHP attributes and doc blocks, which are literally just comments written directly above the function in the code, are parsed to instantly generate the OpenAPI JSON spec.
And the mechanism behind this is abstract syntax tree, or AST, parsing. What's fascinating here is that Scramble doesn't just read the text of the code. It fundamentally understands the structure of the Laravel application.
What do you mean by understands the structure?
It analyzes the route definitions, inspects the request validation rules. For example, if the code demands the payment amount must be an integer greater than 0, and then traverses the AST to automatically map those exact programmatic constraints into the JSON documentation.
So the code physically is the documentation. It's like
Yes.
a self-writing instruction manual.
Hmm.
Imagine building a Lego castle, and the exact moment you click two bricks together, the instruction booklet just prints out the exact step you just took for whoever wants to build it next.
That is a brilliant way to picture it. If a developer changes the validation rule to allow decimal points, the AST parser catches the change on the next build and the OpenAPI spec updates instantly. There is zero drift.
Which guarantees that the clients integrating with the API, whether that's a mobile app developer or a third-party merchant, are always building against the absolute cryptographic truth of what the server requires.
Precisely.
But here's the thing. Processing ASTs, validating idempotency keys, executing eager-loaded ORM queries to MariaDB. All of these operations take CPU cycles.
Yeah.
They take time. And if a user hits that payment charge endpoint, they expect immediate gratification.
Right, they want to see success instantly. This introduces a massive architectural friction point. How do you execute complex, secure business logic without degrading the user experience?
Which brings us perfectly to the fourth pillar, asynchronous processes, the need for speed. The source document lays down an ironclad law here, the 50 millis rule.
It's ruthless.
It says when a user hits the payment charge endpoint, the API must return a 200 OK payment successful response in under 50 milliseconds.
To put that in perspective, the latency of the network round trip alone, just the signal traveling from a user's phone over cellular towers to the data center and back, can consume 30 of those 50 milliseconds.
Wow.
Yeah, so the server literally has virtually no time to think.
And PHP, which is the underlying language of this Laravel framework, is traditionally a synchronous blocking language, right?
Right. Unlike Node.js, which uses an event loop to handle multiple requests on a single thread, PHP utilizes a process manager like PHP FPM. Every incoming request locks down an entire PHP worker process.
Oh, I see. So if that worker is stuck waiting for an external email server to send a receipt, it cannot handle any other traffic.
Exactly. If you get a spike of 1,000 users checking out simultaneously and every worker is blocked waiting on some slow email API, you exhaust your entire worker pool in seconds. The server just stops responding entirely.
So the golden rule stated in the document is never block the main thread. They delegate all heavy I/O, which are input-output operations that talk to slow external systems to the background.
Yes. The main thread executes only the absolute critical path. It validates the sanctum token, checks the idempotency key, and updates MariaDB to paid. That takes maybe 10 milliseconds.
And then for everything else, like sending the merchant webhook or emailing the receipt,
It writes the data payload to a background queue and immediately fires the 200 OK back to the user.
the slide notes the queue system acts as a high-speed buffer, typically backed by an in-memory data store like Redis. Writing a payload to Redis takes fractions of a millisecond. So the main thread serializes the PHP object representing the email task, dumps it into the Redis queue, and literally just considers its job done.
Right, and dedicated queue workers running as completely separate background processes pull those serialized tasks out of Redis and execute them. Those take 2 to 5 seconds.
But I have a major concern here.
Okay, what is it?
By returning a 200 OK to the user before the receipt is actually sent, the system's essentially lying, isn't it?
Well, technically.
I mean, it's like a drive-through window. The cashier hands you your receipt and says you're good to go. That's the 50 meters API response. But the cook in the back is still making the burger. That's the 2 to 5 second background worker.
I love that analogy.
If the grill catches fire, you have a receipt, but no food. What if the email API is down? The background worker pulls the task, tries to send the email, fails, and the task dies. The user got a success message, but the merchant never got the webhook, and the user never got the receipt.
Okay, so in a synchronous system, that failure would crash the checkout process entirely. The user would see a 500 internal server error, their money might be in limbo, and trust is completely destroyed.
Which is worse, true.
Right. In this asynchronous architecture, the system employs graceful degradation and a sophisticated failure diagnostic loop.
Yeah.
This is the fire extinguisher for your drive-thru grill.
Ah, the slide explicitly details this loop. It uses a failed jobs database table. So if a background worker encounters an exception like, I don't know, a connection timeout to the webhook server, it doesn't just discard the task.
No, the worker catches the exception and immediately shifts the payload into what is known as a dead letter queue. In Laravel's ecosystem, that's the failed jobs table. It records the exact timestamp, the entire serialized object containing the user's data, and the full stack trace of the error.
It essentially preserves the crime scene.
Exactly. And the user's experience is totally isolated from this failure. They bought the item, the money moves safely.
And the architecture employs exponential backoff, right?
Hmm.
The worker doesn't just fail once and give up.
Right. It might retry the webhook after 10 seconds. If that fails, it waits 30 seconds, then 2 minutes. It gives the external system time to recover on its own. Only after exhausting its retry attempts does it permanently write it to the failed jobs table.
At which point, the human engineers can inspect the table, read the stack trace, fix the underlying code issue, and then use an artisan command to reprocess the exact payload. The email finally sends, completely seamlessly from the user's perspective.
This is the absolute essence of resilient distributed systems. You anticipate failure, isolate its impact, and build automated recovery mechanisms.
It's brilliant. But, relying on capturing errors in production, even gracefully, is a terrifying way to run a financial platform. You want to prove the logic is flawless before it ever deploys. Which brings us to the third pillar, quality assurance. The automated QA workflows.
Right, we transition from reacting to failures in production to mathematically preventing them during development.
The document outlines an extract, transform, and import pipeline. Step 1, extract.
Right.
We use the Scramble AST parser we talked about earlier to generate the open API JSON file.
Yep.
Step 2, transform. An artisan command, php artisan postman.generate, converts that specification into a Postman collection.
And Postman is the industry standard for API testing. It creates a sandbox environment where developers can simulate complex request lifecycles. But tests are only useful if they reflect reality.
Right. If you hard-code a test to always send a $10 payment using the exact same static credit card number every time, you are only proving the system works in that one highly specific scenario.
You create massive blind spots. What if the API fails when a user has a hyphenated last name or when the payment amount exceeds 4 digits?
So the architecture demands a dynamic test data pipeline. The slide shows Postman utilizing pre-request scripts running inside a V8 JavaScript engine sandbox. Before the test even touches the API, it runs a script using faker.js.
And instead of a static name, it injects a randomly generated full name. Instead of a fake string of numbers, it uses a dynamically generated, valid-looking credit card number. It dynamically generates highly realistic, edge case-heavy payloads.
It also dynamically generates the expected mathematical outcome. The script uses math.random to generate a base amount and saves it as a local environment variable. It sends that randomized amount to the API.
And then we hit the post-response assertion. This is the absolute core of the QA workflow.
Right, so let's translate this syntax on the slide, pm.expect and so on. What does this mean?
The PM represents the Postman API sandbox. The assertion isn't just asking if the server returned a generic 200 OK. It is explicitly commanding the test. Take the JSON response from the server, drill down into the data object, extract the amount field, and strictly equate it to the randomized number we saved in our environment variable before the test started.
So what does that all mean in plain English? It's like a crash test dummy factory, right? Instead of just running the same dummy into the wall at the same speed every time, this dynamic pipeline randomly changes the weight of the dummy, the speed of the car, and the angle of the crash on every single test run to make sure the airbags always deploy.
That is exactly what it is. If the script generated a payment of $4,921.34, it demands the server's database confirm exactly $4,921.34. If there is even a floating point precision error in the PHP math logic and the server returns $4,921.33, the assertion fails immediately.
Boom, test fails.
The continuous integration pipeline halts, and the deployment is blocked. The bug never reaches production. This level of contract testing guarantees that the external behavior of the API perfectly matches its internal business logic, regardless of the chaos of the input data.
Amazing. So we have an architecture with passwordless cryptography, highly optimized relational database logic, asynchronous worker queues preventing thread blocks, and dynamic test assertions guaranteeing mathematical accuracy. It's a perfected digital blueprint.
It really is.
But it actually has to exist somewhere. The code must be executed on physical hardware. We arrive at the final pillar, infrastructure.
The foundation that dictates whether the system can actually scale to meet the demands of real-world traffic.
The document describes a containerized production environment managed by a caprover orchestrator on a virtual private server.
Containerization, utilizing Docker under the hood, is the paradigm shift that enables modern cloud infrastructure.
How did it work before Docker?
Historically, if you had a physical server, you installed an operating system, and then you installed PHP, MariaDB, and a mail server directly onto that shared file system. They were hopelessly tangled.
Like spaghetti.
Exactly. If the mail server required an update that changed a shared system library, it could inadvertently break the database.
Ouch. CapRover abstracts away the raw Docker complexities, but what Docker is actually doing is utilizing Linux kernel features, specifically namespaces and C groups, to isolate these processes.
Right. Namespaces provide the isolation. When the PHP application is placed in a container, the Linux kernel gives it a dedicated namespace. From the application's perspective, it believes it is the only process running on an entirely independent machine.
So it's completely blind to everything else.
Exactly. It cannot see the MariaDB container. It cannot access the mail server's memory. It has its own isolated file system and process tree.
And key groups, which stands for control groups, limit the resources. If the PHP application has a memory leak and tries to consume 100% of the server's RAM, the key group acts as a hard ceiling. The kernel kills the PHP container before it can starve the MariaDB container of resources.
Which is fantastic for stability. The diagram illustrates 4 distinct containers orchestrated here. NGINX acting as the entry point, the Apache PHP container running the Laravel codebase, MariaDB for persistent storage, and an IRED mail server container for the outbound magic links and receipts.
And NGINX operates as the reverse proxy and load balancer. It sits right at the edge of the network, intercepting every single incoming HTTP request. But if a massive spike in user traffic hits, say, a viral marketing campaign drops, a single server, even a well-containerized one, has physical limits.
It does.
So the scaling strategies here offer 2 paths, vertical and horizontal. Let's start with vertical.
Vertical scaling is the simplest. The document notes it requires 0 configuration in CapRover. You simply provision a larger instance from your cloud provider, moving from 4 CPU cores to 16 or 8 gigabytes of RAM to 64. You reboot the VPS and your containers suddenly have vastly more headroom.
But there are hardware realities, right?
Yeah.
You hit the limits of UMA nodes, non-uniform memory access architecture. Eventually, adding more CPU cores doesn't yield proportional performance gains because the physical distance between the CPU and the memory modules on the motherboard literally creates latency.
Exactly. You just can't scale vertically forever, which forces the transition to horizontal scaling, scaling out.
The diagram shifts from one massive server to a cluster mode using Docker Swarm. Suddenly, there are multiple app instance servers sitting behind the NGINX load balancer.
And NGINX utilizes algorithms like round robin, which passes requests sequentially, or least connections, passing the request to whichever server is currently least busy to distribute the traffic across the swarm.
But the slide includes a massive, bolded warning for horizontal scaling. It mandates. Crucial rule: horizontal scaling requires stateless application design. What does that mean?
This is the defining challenge of distributed computing. If a user logs into server A and server A stores that login session in its local memory, what happens when the user clicks the next button and NGINX routes that subsequent request to server B?
Well, server B has no record of the user. It throws an unauthenticated error and kicks the user back to the login screen. The state was local, and the infrastructure is distributed.
Exactly.
So it's like, okay, think of a coffee shop. If I go to a coffee shop every day, vertical scaling is upgrading to a super barista with a massive brain who remembers my exact order every time. That's stateful.
I like this.
Right. But horizontal scaling is hiring 5 normal baristas. But to make that work, none of them can rely on memory. I have to physically carry a card with my exact order on it, so that's stateless, so any of the 5 baristas can serve me perfectly. And that card is our sanctum token from earlier.
Yes. That is exactly how it works. That ties the whole architecture together perfectly. In a stateless design, the server remembers absolutely nothing. The client, the user's browser, holds the cryptographic token. With every single request, the client presents the token to whichever server NGINX assigns them to.
And because the token is signed with an HMAC SHA-256 hash using a shared secret key, server B can look at the token, perform the mathematical hashing algorithm locally, and verify its authenticity without ever needing to query a centralized database or communicate with server A.
The math itself proves the state. This means you can scale horizontally from 3 servers to 3,000 servers, and the architecture remains flawlessly, perfectly synchronized.
It is an incredibly elegant synthesis of cryptography and infrastructure. Wow. Okay, let's bring this all together. The final slide is a master diagram, the final schematic, an enterprise-grade API topology. Let's trace the exact path of a single payload through everything we've just dissected.
The complete life cycle.
Okay, the client clicks pay. The JSON payload traverses the internet and hits the CapRover NGNX proxy. This is our infrastructure pillar. NGNX calculates the least connections algorithm and routes the request into the optimal PHP container namespace.
The payload hits the security pillar. The Sanctum middleware intercepts the HTTP headers. It extracts the bearer token, executes the SHA-256 hash, and compares it to the token cryptographic signature. The math validates. The bouncer steps aside.
The request drops into the core logic pillar. The payment charge endpoint, whose precise requirements are continuously documented by the Scramble AST parser, validates the idempotency key. It instantiates the Eloquent ORM, executing a highly optimized, eager-loaded SQL query to update the MariaDB relational tables. The state officially changes to paid.
And at that exact millisecond, the architecture splits, downwards into the async pillar. The main thread serializes the email receipt payload and pushes it into a Redis queue. A background worker picks it up and begins communicating with the iRed mail container. If it fails, it cascades into the failed jobs dead letter queue for exponential backoff retries.
But simultaneously, shooting to the left, the main thread instantly returns the 50 millisecond 200 OK response to the user. And in the development pipeline, that exact JSON structure is intercepted by the Postman V8 engine, where the pm.expect assertion rigorously verifies that the dynamically generated faker.js math matches the server output flawlessly.
It was a symphony of microservices, asynchronous queues, cryptographic statelessness, and dynamic QA assertions. A beautiful, flawless machine.
And you, our listener, you now possess the detailed mental map. When you interact with a major digital platform tomorrow, you aren't just pushing a button on a screen. You are initiating a vastly complex, highly choreographed execution of computer science that secures your identity, optimizes for impossible speed, and seamlessly distributes computation across thousands of hidden machines.
It fundamentally changes how you perceive the friction or lack thereof in modern software. But I may leave you with a final thought to mull over.
Please do.
We've spent this time examining the logic of horizontal scaling, the elegance of stateless tokens, and the resilience of background workers catching their own software failures. And it is remarkably robust code, but consider the physical reality beneath the code.
Right, the hardware.
Exactly.
Yeah.
All of these Docker containers, the CapRover orchestrators, the NGINX load balancers, they ultimately run on silicon inside server racks in massive data centers. What happens when the underlying physical infrastructure goes down? When a backhoe severs a major fiber optic trunk line or a regional power grid collapses?
It's a house of cards in a way.
So as you browse the internet tomorrow, experiencing instant, flawless transactions, ask yourself, how many redundant availability zones, automated network routing protocols, and entirely mirrored data centers are secretly catching the physical failures of the real world, ensuring this digital architecture never blinks without you ever knowing?
The brilliant code is ultimately hostage to the fragile physical world it sits on. The visible hides the invisible. Thank you for joining us on this deep dive into the unseen architecture. Keep questioning the invisible machinery around you. We'll see you next time.